Okay, so let's keep going with our review of the material you should know from discrete structures. I'm moving on to Hein chapter 1.2. Here's the same disclaimer as from the previous slides. This is material you should know already from discrete structures. And if you're not comfortable with this material, it's time to retake discrete structures rather than trying to make it through foundations. So we're going to go on to chapter 1.2 about sets, and let's start with the definition of a set. So suppose that S is a set and S is the set XYZ. Wow, 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 wow. Okay, so let's keep going with our quick review of the material that you should know from discrete structures that's most important for this course. Now we're on to chapter 1.2 of the Hein textbook, and same disclaimers as before. This is material you should know already from discrete structures, and if you don't, then you need to really think hard about whether you should be in this class. So 1.2.1 has the definition of a set. I'm going to assume you already know what a set is, but let's suppose that S is a set and S is this set XYZ. We use this notation, this little element notation, to say X is an element of S. I'll use a line through that little element symbol to say A is not an element of S, right? We can also, of course, use these ellipses to indicate that there are things missing in the set that we just want to include following the pattern. I'm going to use this symbol to represent the empty set, right? So here's another way to represent the empty set. And it's really important whenever you are working with sets, if you see the empty set symbol, I really recommend, if you are not totally comfortable with sets, that you just replace it everywhere you see it with the empty set braces, because that really will help you. Of course, if we have a set, the order of the elements of our set doesn't matter, so the set containing the elements A, B, and C is exactly the same as the set containing the elements B, A, and C. If you have a set that just has one element, it's called a singleton. And again, I'm trying to stick as closely to your book as possible to help you out here. So while everybody says sets do not have repeated occurrences of elements, this is totally legal according to your book to say this is my set, right? R, comma, O, comma, W, comma, A, comma, N, comma, U, comma, N, comma, I, comma, V. But what this really represents, these braces really represent this same exact set where the element N only occurs once. Because of course, even though we repeated it inside the set symbols, there are no repeated elements in a regular set, and so this is equivalent to this. We've already talked about the integers. I'm going to introduce this capital Z symbol for the integers, which your book also uses. There are also the natural numbers. And so we're going to use this capital N for the natural numbers. And in your textbook, the number 0 is part of the natural numbers. You may have learned that 0 was not a natural number, but for the purposes of this class, 0 is a natural number. And we'll just note that some sets are indeed finite while others are infinite. These two sets happen to be infinite. We can define sets by properties. So for example, here's a definition of a set. This says the set of all items S, of all elements S, such that S is an element of the integers and S is also greater than 100. So here's a more colloquial way of saying that, the set of all integers that are greater than 100, right? Here's a similar set, S, the sets of all elements S, such that S is in the natural numbers and S is greater than 100. So the set of all natural numbers greater than 100. And if you think about it, these are both the same thing, right? And here's another set. We could say the set of all students S such that S is enrolled in foundations and S is over 21. So all students enrolled in foundations who are over 21. We're going to use the notation that your book uses for subset. So it's kind of this sideways U with the equal sign to mean subset. So if a set is a subset of another set, that means that all of the elements in the first set are included in that second set. So the set containing the elements 1 and 2 is certainly a subset of 0, 1, 2, 3. The set containing those elements 0, 1, 2, 3. Of course, any set is a subset of itself. So here I show that the set 0, 1, 2, 3 is indeed a subset of itself. Your book uses the not subset symbol that looks like this. So 2, 3, 4 is not a subset of 0, 1, 2, 3. I'm a little bit annoyed by the fact that there is no kind of equals sign under here because we also talk about a proper subset. And a proper subset is a subset of, is a subset where the first thing is a subset of the second and they are also not equal, right? So if we have this subset notation without that little equals sign bar on the bottom of it, it means it's a proper subset. So for example, 0, 1, 2, 3 is not a proper subset of 0, 1, 2, 3, but it is indeed the case that 1, 2, the set containing the elements 1 and 2 only, is a proper subset of the set 0, 1, 2, 3. And here's just another example of something that's not a subset, right? So 0, 1, 2, 3, 4 is not a subset of the set 0, 1, 2, 3. And the really super important thing to remember that you really, really, really need to make sure you totally get is the difference between this element and subset symbols and what they mean. So 1 is indeed an element of this set, but 1 is not a subset of this set. You can only have a subset if you're a set. So the set containing 1 is indeed a subset of the set containing 0, 1, 2, and 3. But this number 1 by itself is not a subset. All of these statements should make sense, so let's just go through them real quick. Let's suppose that S is the set containing 3 elements, A, B, and C. A is indeed an element of S. The set containing A is a subset of S, and in fact, it's also a proper subset of S. But the set containing A is not an element of S, right? Because that would require us to have a set that had a set in it. A is not a subset of S. The empty set is indeed a subset of S because everything in the empty set is also an S, but the empty set is not an element of S. Let's talk about 1.2.2. So we've got these Venn diagrams of union and intersection. You should be pretty familiar with union and intersection. So union is just the set of all, if you have two sets, the union of those two sets is the set of all elements that is in either. The intersection of those two sets is all elements that appear in both sets. So for example, if here's our set A and here's our set B, this is the union and the intersection of those two sets. And of course, we can draw these Venn diagrams for A union B and an A intersect B. Another piece of notation that the book introduces in this chapter that you may or may not be familiar with, but it's pretty straightforward, is the difference between two sets. So we can talk about the set A minus the set B. And that is just all elements that are in A and not in B, right? So if you have the difference between two sets, it's the set of all elements that are in A but not in B. We also have the complement of a set. So when you talk about the complement of a set, you need to have a universe. You need to talk about what is the world in which I'm going to figure out the complement? Because the complement is, of course, everything that's not in the set. So, for example, if we think about the set S, which has these elements in it, in the universe of all one-digit natural numbers, then the complement of the set, and I'm writing the complement using a prime symbol because that's what your book does. A prime, the complement of A, is all those one-digit natural numbers that don't exist in here. And you should also note that there's other stuff that I'm not actually showing you from this this section of the chapter that you do need to know. So just review the chapter. I'm trying to just go through real quick the highlights of the chapter, right? This is a review. Remember, this is a review. Okay. So here are two tables straight out of the book that talk about the properties of union and intersection. So let's just look at them for a minute. You should look at all of these things and say, yep, that makes sense. So if you union the empty set with anything, you get the original thing. So A union the empty set is A. If you intersect the empty set with anything, you end up with the empty set. Union is commutative and associative, so is intersection. If you take the union of something with itself, you get that thing again. Similarly, if you take the intersection of something with itself, you get that thing again. And then there's this final one. A is a subset of B if and only if A union B is the same as B. So you need to think about that for a minute. And similarly, A is a subset of B if and only if A intersect B is the same exact thing as A. Let's go on to 1.2.3, just talk about counting briefly. So if S is a set, then we're going to use this notation to represent the size of S, these kind of bars around the S. So for example, if S is the set containing A, B, C, T is the set containing D, C, F, G, Q is the empty set, and R is this weird set. Look at R. It has 1, 2, 3, 4, 5 elements in it. The first element is a set containing only one item. Then there's 2 elements that are just regular elements. The fourth element is a set, and the fifth element is just the letter F. So if we look at this, the size of S is 1, 2, 3. Yep. The size of T, 1, 2, 3, 4. That makes sense. Of course, the size of the empty set is 0. And the size of this last set R is how many elements are in R. This set containing just A is one element. This is one element, the item B. C is one element. This set containing 2 elements is just one thing when we're counting everything up in R. So we have 1, 2, 3, 4, 5. The size of R is 5. And finally, this is out of the book again. If you want, you can actually say, what's the size of the union of 2 things? So if you union 2 sets together, how big is it? Well, the resulting set is however big A was, plus however big B was, subtracting off however many things they had in common.